All right. Sometimes you're choosing things, but you have more than one decision to make. So what we're going to find is some of our strategies that we had in permutations, they come over to combinations as well. Sometimes you can have cases with combinations. Sometimes you can have spaces with combinations. And in this case, what we have is you've got to hire 3 cashiers and 4 store clerks. So there's 2 main decisions that need to be made. But there's combinations for both of those decisions. So you can draw out 2 main spaces for our decisions because we need to pick cashiers and store clerks. Since there's 7 applicants for cashier and you need to choose 3 of them, the order doesn't matter. There'd be 7, choose 3 for cashier. And for store clerks, there's 8 applicants and you need to choose 4 of them. So that would be how many ways you could choose your store clerks. And what are you going to do with these 2 numbers with spaces? What did we do in between? Did we add, subtract, multiply, or divide? We multiplied.
Why?
Because every time you did spaces, we multiplied, right? This many, because for every group of 3 cashiers, they could be mixed with any of the 4 groups, 4 that were in the store clerks. So each unique group of cashiers could go with each unique group of store clerks, and the way that would show up on a tree diagram and the way that that would work out is if you would have to multiply. We'll steal the answer from over here, 2,450. So this also comes up fairly often. We see that it's a combination question because order doesn't matter. But because we have more than one decision to make, we would put them and multiply them together. So the questions for this one are 12, 13, 14, 15, and 16. And we're going to do 15 together right now. So we'll pull that up. Now for A, on an exam, if they gave you A, they would say solve each equation for n algebraically. Then what you would do for A is you'd go to your formula. Your NCR formula is on your formula sheet. So it would be n factorial over n minus 2 factorial equals 28. And this practices our factorial work again. How did we get rid of factorials when we're dividing? Expand the top one. And why did you expand the top one and not the bottom one? Because it's bigger. So what we do is we start expanding the top. We're going to get n minus 1. And when we get to n minus 2, we're going to stop because we have an n minus 2 on the bottom. Still have a 2 factorial. Are you all right if I just write that as 2? Because 2 factorial is just 2, equals 28. And these n minus 2's will cancel. I still have a fraction on the left. How can I get rid of that 2 on the bottom? Times by 2 on both sides. On the top here, when I expand it, I'm going to get n squared minus n. And over here, when I multiply by 2, I get 56. And then we'll bring it over and factor. And what's the last thing you have to remember? You can't do negative factorial, so if I try negative 7 in the beginning, sure enough, there would be a negative factorial. but 8 would be fine, so this one is extraneous. Put an X through it. And n equals 8 is the only answer. For the other ones, if the numbers are not nice, then a guess and check could start to come into play. So for C, 4 choose something equals 6. That I would just guess and check until you find it, because the formula will not help you. There won't be things to simplify. And guessing and checking on this one with either your calculator or by hand, 4 factorial over 4 minus something factorial has to equal 6. After guessing and checking, you're going to find out that that's 2. I'm going to show you a method for B that would work, but guessing and checking is what would be expected for B. The only time they're going to give you one algebraically is if it's a 2, because it's nice numbers. Because look what happens in B. In B, if I would do n factorial over n minus 4 factorial equals 35. And I expand the bigger one, which is n factorial. I'm going to get n times n minus 1 times n minus 2 times n minus 3 before I get n minus 4 to cancel out. And on the bottom I have 24 equals 35. If I expand that, I'm going to get an n to the power 4. And on this other side, I'm going to, when I multiply, now if you really like mathematical pain, you could multiply this out. You'd get an n to the 4. You could multiply 24 times 35 out, get a big number, bring it over to the other side, and use Chapter 1's factor theorem to try and factor it with synthetic division. And after you've factored one factor out with an n to the 4, you'd be left with an n to the 3, so you would have to use the factor theorem again and use synthetic division again and see if you could factor it one more time. And you might get a bunch of extraneous roots, and it would be very nasty. Now the nicer thing to do in this situation is to recognize these 4 numbers are consecutive, because they're always one less, one less, one less, one less. They're all multiplied together. Could I break up the 24 times 35 to get 4 numbers multiplied together? Now there's more than one way to do that, but how could I break up 24? 4 and 6. Okay? And how could I break up 35? 5 and 7. Could I write those, are they all in a row? Sure, if I rearrange them, I could write 7 times 6 times 5 times 4. And n happens to be the biggest one. And that causes a lot less mathematical pain than the other way. And that would be a systematic way that you could solve that one. But guessing and checking here too. 5 choose 4 is going to be 5. 6 choose 4 is not big enough. 7 choose 4. And you're going to get it not very long by guessing and checking either. So now if you take out your handout, we also have some additional combination notes there, and we're going to do those as well.